much. So it's a pleasure to be here. Pleasure to be here in person, even though I had to put on pants and drive across the bay this morning. It's much nicer being in person. So I've showed versions of this chart a number of times before, but it's really exciting to show this chart now because instead of this being something that we're going to do in the future that's going to be really cool, it's something that we've done and are doing now. And it is indeed really cool. Artemis and LADEE and LRO and all of the other assets that we have at the moon now and recently are a really amazing team to study this coupled exosphere surface environment. So the lunar exosphere, this beautiful tenuous collisionless exosphere, this is sodium as seen from the Earth, D-line emissions seen optically. Beautiful, beautiful kind of thing. Since I'm a physicist, I'm going to take this beautiful exosphere and turn it into an ugly flowchart. And I did not correspond with Rick before giving this talk, but I noticed that Rick and I have almost exactly the same list of processes and sinks and sources here, so I'm glad we didn't disagree with each other too much. But basically, as Rick went over, you've got all these sources of the lunar exosphere, some of them exogenic, some of them endogenic. Once you get them into this box, there's this constant recycling with the surface. Some species that don't adsorb to the surface just bounce off and thermally accommodate. Some things stick for longer and get released by a variety of processes. And there's basically only two ways out of this box. You can either gain enough energy when you come off of the surface to escape the lunar gravity as a neutral, or you can get ionized and you can get swept away by the plasma. Now, not every ion gets swept away. Some of them get bashed right back into the surface. But ultimately, this is one of the biggest loss processes. So I throw this up here not to prove my skill at making flowcharts, which is obviously limited, but to talk about multi-spacecraft observations, because we measure everything here. LADEE, of course, is tailored to measure the neutrals, including the escaping components. It also has a dust instrument, which measures things relevant to some of the sources. By looking at different species, we can measure things relevant to internal outgassing. Now, if we add Artemis in here, we measure, of course, the pickup ion escape. We also measure the solar wind source of some of these species. And we measure the sputtering term from the surface. Now, let's not forget that LADEE also measures ions, so we've got a little bit of help in this regard. And let's not forget LRO and N-cubed and all the other lunar assets that we have around the moon, both currently and recently. Because with these, we can get an angle on the surface chemistry, and very importantly, we can get an idea of what's going on with the temperature at the surface, which I did not realize in advance how important of a term this is, but it's very important indeed. You'll notice that I have almost everything in here colored, except maybe primordial comets. We don't really have anything that measures those, or maybe we do. So my point in showing this is to show that it's a very complicated coupled system, but we actually have all the measurements to do this now. So it's a really exciting time to be working on this problem. I'm going to show a couple examples of actual data. I won't be quite as shy as Rick was about showing data, but also don't want to scoop too many people. So this is helium. The red curve here is the helium that's delivered by the solar wind, as measured by Artemis in the form of alpha particles. And the black dots are measurements of the neutral helium made by the mass spectrometer on LADEE. I think you'll agree that this is a remarkable correlation between two completely different kind of instruments on two completely different spacecraft. In fact, you rarely see this kind of thing in space physics. And what it's telling you is that the solar wind is the ultimate source of most of the helium exosphere of the moon, which we kind of knew in advance, but it's still remarkable to see it confirmed so well. Something that's a bit more complicated because it has a number of sources is the sodium, which Rick also showed. This beautiful UVS data from Tony Colifrate with the two different colors showing sodium at two different local times. The eye is very good at finding correlations, some of them that are real and some of them aren't. But I think you'll all agree that there's a real dip in all of these quantities as you go into the magnetotail, as both the proton flux and the alpha particle flux goes down, and you turn off this sputtering term. There's obviously a lot of other things going on here, micrometeorites, et cetera, but it's a hint that the solar wind has an effect. As I said, we also measure the escaping ions from this exospheric surface combination. I've shown these kind of plots here before, where these are the vectors of the pickup ions forming this big escaping plume out from the moon. This is in the solar wind, where the gyroradii of these things are huge compared to the moon. So the moon's basically a little point source down here, and you've got a big plume of escaping stuff coming out to the sides, depending on the direction of the electric field. In the magnetotail, the flow velocity and the electric fields and everything are smaller, so it's a more diffuse, spread out plume, as shown in these simulations by Andrew Poppy. One thing we discovered this year that's a little bit new is that these escaping ions actually carry enough density that they affect the magnetic fields. They drive a current system. So the moon is actually in some ways behaving like a very, very weak comet, which is fun. I like to talk about the moon not just as the moon, but in context. And again, this kind of echoes one of Rick's slides. But the moon is really in an interesting corner of parameter space up here. It's relatively large compared to the plasma scales, but it doesn't have very much conductivity. It doesn't have very much that affects the solar wind other than just being a solid obstacle. So you can turn the dial in two different directions. You can turn down the scale size and get towards these objects like Phobos and Vesta, and even smaller. This is one of the primary tasks that we've set ourselves on the Dream 2 survey team. But you can also turn the dial in a different direction and turn up either the intrinsic conductivity of the object or turn up the amount of atmosphere and ionosphere you're producing that also affects the solar wind and turns it from a simple kind of absorbing interaction into something that looks more like a magnetosphere. You can turn up both of those dials and you end up with something that looks like a spacecraft. So here's the wake. This is the dominant feature of the lunar plasma environment. This is a simulation by Mats Holmström from Kiruna. Of course, what's happening is the solar wind is going from left to right across here. It's all getting absorbed and or neutralized at the dayside surface. And so you have this trailing wake in the density seen in two different cuts here. As the plasma tries to fill in that void, it pushes the magnetic field in front of it. And so you get a compression in the magnetic field in the center of the wake. So this is the simulation, but now we have enough data from Artemis that we can show this in data. And I apologize that the color bar is not the same now. Not everyone agrees on what color bars should be. But you're seeing exactly the same two cuts. But now this is a synopsis of hundreds and hundreds of orbits of Artemis data. And you're seeing the wake in the density, and they drop out in the density. And you're seeing the same compression in the magnetic field as this plasma pushes the field into the void. And it's remarkable how well the systematics match up with the model. Now this is the average lunar wake. You'll see that the magnetic field here is going up to about 30% above the undisturbed upstream value. But this is just the average. There are times when the compression is much more significant than this. And here's one of these cases. This is a paper by Andrew Poppy showing a case where this increase in the magnetic field now is not 30%, it's 150%. So just the presence of this solid absorber in the solar wind and the effects of that plasma filling in the void are creating a compression in the magnetic field that is greater than a factor of 2. That's really a remarkable kind of a thing. Usually it takes something like a shock to do something that significant to the magnetic field in the solar wind. But all we're doing is absorbing some of it. Here's the model comparison here from our new survey postdoc, Shahab Fatemi. We've also been doing some paper and pencil theory, trying to understand what we're seeing at the wake. This is another Artemis flyby now, case with much, much smaller effects in the magnetic field. The magnetic field is really controlling things and not getting pushed around in this case. It's a little bit simpler to do theory. And you can see that we can actually come up with a model that fits the data very well, just using simple theory in this case. You'll notice that outside of the wake here, we've just been talking about the cavity wake behind the moon, but actually outside of this wake, there's some interesting little wiggles in the magnetic field. Those are probably driven by protons that are reflected from crustal magnetic fields on the day side. In this case, you're just seeing wiggles, but there are cases when we see much larger perturbations. Here's one of those cases. These features seen outside of the lunar wake have been seen back to the Apollo days. People have called them limb compressions. People have called them limb shocks. I'm going to tentatively call them limb shocks because we see signs that they are, in fact, a shock. If you look down here in the magnetic field, you can see this very sharp amplification in the magnetic field, which corresponds to an amplification in the density by over a factor of 2, and the flow velocity is getting deflected. And if you look up here, this is the spacecraft trajectory. We're coming around the side of the moon, about to dive into the lunar wake, and you see the flow getting diverted outwards from the wake. And if you trace back upstream to what that's being launched from, it's being launched from this region of strong crustal magnetic fields here, shown in grayscale, and it's probably being driven by these reflected protons, which are all getting spattered off of this crustal magnetic field region. It's really neat because this is a really, really small scale shock, if it is indeed a shock, perhaps one of the smallest in the solar system. Of course, what you'd really like to do is you'd like to get down into this region where the protons are actually getting reflected and see what's actually happening here. And there are a few times on the Artemis mission where we actually do this. So here's a case where we fly through at very low altitude. Now, the previous flyby was at 500 kilometers or so. This is down at 20 kilometers. Now we're flying the opposite direction from right to left instead of left to right across this thing. But we're seeing some of the same things. We're seeing the solar wind density jump up as we go over this thing. But now we're actually in the soup. We're actually seeing these protons being reflected off of magnetic fields all around us. And you can see that just in terms of the density that they form in red here. That density is around 20 or 30% of the solar wind, and it's diverging from the surface as it comes at us. So it's at least that much being reflected at the surface. You can see that in these vectors here. What these vectors show are the velocity of the reflected protons on average that are coming up at us. And what you see is really quite remarkable, in my opinion. They're actually coming all up at the spacecraft from this tiny little magnetic source here. There's a huge complex of strong magnetic fields up and to our left, but that's not where they're coming from, because we're flying over here. And we're still seeing this dramatic reflection of protons. And look at what it's driving in the magnetic field. This is the undisturbed interplanetary field over here for context. And then look at this crazy thing. Now, this is not a direct measurement of the crustal magnetic fields. These are actually distorted solar wind fields that are getting wrapped up around this interaction. But just imagine if we had flown up here. We're down at this little guy down here. I thought it'd be fun just to finish up by showing the context of this observation. So I got online, and I found that you can get this wonderful browsable image search from the LROC team of these amazing images from the LROC camera. This is really a wonderful feature. I encourage people to play around with this and just, look at what's in there. So this is where we're seeing all this proton reflection coming from. As you recall, the strong magnetic fields are actually up in this region. And it turns out that this region has been comparatively well studied, because if you have very good eyes here, you can start to see that there's something a little bit funny going on here in this terrain. So if we zoom in on that, you'll see that this is a region that Dave Blewett studied in detail. And he studied it because there's these very strange albedo markings on the surface. These, of course, are the well-studied lunar swirls. They seem to be very well correlated with regions of crustal magnetic field. One theory for their existence is that they represent shielding of the surface and differential space weathering of the surface. If we can look at these reflected protons and see what that's telling us about the shielding at the surface, it'd be really neat. Now, again, that was up here. We're down here. Is there anything going on down here? Well, maybe. It's a little bit harder to see what's going on because there's all this bright ejecta over here. But to my eye, at least, in the floors of some of these craters, you can see some interesting optical markings. Now that I've showed my ignorance to all the spectroscopists in the room, I'm actually on time, and I might even have time for questions. But if we can learn how to read these observations of reflected protons and understand what's really happening down at the surface, then I think it would be really cool. So I'll finish up here just with a note about the future of Artemis. The future hopefully will extend for a long time because the orbits are very stable. We don't require a lot of station keeping. Both spacecraft and all the instruments are healthy. And the moon is a heck of a good place to do not just lunar science, but magnetospheric and solar wind science. So I hope that we're going to continue to operate around the moon and collect data for as long as possible. Thank you very much.
Excellent. Thanks very much. I see hands already. Way in the back. Thank you for waiting for the microphone.
Russell Cox, Fletcher Drink. Is this on?
Could you hear it?
I could hear that.
Okay, great.
Good, thanks. There we go. Russell Cox, Fletcher Engineering. So what would your data set look like if you had like 50 Artemises instead of 2?
Much more complete?
Well, yeah, would there be things you could see better? I mean, that's a valuable thing to strive for in the next decade?
Well, it all depends on the orbit, right? The thing that limits us in the Artemis orbit is that we get a limited view of the interaction. Having 2 points is better than 1, so having N is better than 2. But there would be more value to having additional observations in unique orbits than just having them in the same orbits we have now, I would say.
Another question, Maria.
Yeah, Maria Zuber, MIT. I vaguely recall that Artemis was going to try to make an estimate of lunar mantle conductivity. Have you done that?
No, we've had a couple people take a pretty good crack at that, and it's been difficult because we don't spin very long close to the moon in each orbit. So you can't do the kind of very long baseline stuff to look at all the frequencies that you'd like to look at. There are people at Berkeley, actually, there's a graduate student working on it very hard right now, trying to do a real model of the plasma and the lunar conductivity all together. But it's been hard work, and we're not quite there yet.
Don't see any other questions? No more? Okay, wonderful. Thank you so much. I appreciate the talk.